Hello everyone, so today we can talk about exam 2 from 203 in the 2019 exam on this fine evening. And so there's only one problem here, which is kind of nice, so let's look at it. At a given instant, a point P on the disk rim is the same horizontal level with the center of the disk. At the same instant, this rod, which is this entire thing, is turning around the vertical axis at constant angular velocity omega 1 equals 3 relative to the Earth. So from that statement, we can first draw our ground frame. So this is the Earth frame where everything is with respect to. So we can write it as E1, E2, and then from right hand rule, we have E3 hat, right? Because we curl our fingers from E1 to E2. Our thumb of our right hand should be pointing in the direction of E3. We also know that this is a constant angular velocity, so omega 1 equals 3. And this means omega 1 dot equals 0. Also at the same instant, the disk is rotating at omega 2 equals 4 with omega 2 dot equals 2. I guess I should mention this is rad per second because this is not the same as if there is revolutions per second. This is rad per second squared. Radians per second squared. And then omega 2 dot is given to be 2 radians per second squared. And this is relative to the rod. So this disk is spinning relative to the rod, which is rotating about this axis here. Suppose reference frame E is fixed with the Earth, which we already drew. Using BKE or kinematic expansions, find the velocity and acceleration of point P at this specific instant. So I will do this problem with first the BKE approach, and then we can do the same thing with the velocity kinematic expansion stuff. Okay, so the first thing of any problem is to make our reference frames. So I'm going to so the question is how to make the reference frames. So we have two rotations that are complex, right? Because one, this omega 2 rotation rotates with respect to this rod, which rotates with respect to the Earth. So I'm going to introduce two frames because I have two unique rotations. So the first frame I'm going to introduce in the rod. So I'm just going to center it here. So I'm going to have it going up this way and then this way. So this points along this rod part. I'm going to call this A1 hat. And then I'm going to call this A2 hat. And then have A3 hat based on right hand rule will point this way. So A2 hat points straight up. And from right hand rule, curl your fingers from A1 to A2. Your thumb points in the direction of A3. It's kind of going out in this direction. So yes. And then we also want another frame for the disk, so I'm going to use a different color for that. So we probably want to center it here because that's kind of it's just an easier location to pick. And then I'm going to have a trick is always to have one of the unit vectors pointing to the point of interest. Okay, that's a little too light. So I'm going to have one unit vector pointing towards point P at all times, and I'm going to call that B1 hat. Then I'm going to have another one perpendicular. Perpendicular to B1 hat, and I'll call that B2 hat. And then B3 hat is pointing out, right, of the disk from right hand rule, so it points out this way. Okay, now we have our frames. So the way to do BKE is you start always with the position vector from some fixed point O to P. So point O is fixed with respect to the Earth. I think you're given, okay, yeah, so we're given that the length of this rod, so from here to here, is 2 meters. That's what's drawn here. And we are also given that this length is 1.5 and this length is 0.5. And the disk radius is also 0.5 from this information here. So I'm just gonna, okay, so what I'm gonna do is just refer to this as like L, say, and then I'll refer to this as D1, and this one is D2, and then refer to the radius of the disk as R. Just so I can have some like variables, because it's a bit annoying to have to write the two, 1.5 and 0.5. So what's the point O that is fixed in the E frame? So you can pick obviously this point here or this point here. Like, you could pick literally wherever, right? That's not moving. But you're obviously only given dimensions from here to here to here. So it would make the most sense to pick your O as being at this point, at like the origin of the A coordinate system. Because this point is not moving, right? It's just the point here, and even though like the disk or the rod is like rotating around, this point here remains fixed in the E frame. It's not moving. So I'm going to pick that as my point O. So I can then write the direction from O to P as we first go a distance L in the A1 hat direction. And then we go up 1.5. So we go up D2, right? I should keep that. So we go this way and we go up D1. Okay, maybe it's easier if I just make these completely. I'll just call those variables H and then D. Okay, and then I go up in the A2 hat direction, a distance H. And then I go a distance D in the negative B3 hat direction, because I'm going this way. And let's write that as negative B3 hat. And I'm also going a distance R B1 hat. So I'm going from here to here to point P. So that's going to be R B1 hat. And then A3 and B3 also point in the same direction. So we can rewrite this as minus D A3 hat. This is just because the rod is like just all at 90-degree angles, so A3 hat and B3 hat point in the same direction. Okay, so the way to do BKE then is to start the differentiation process. So the velocity is derivative of the position. So it means you take the derivative of ROP with respect to the frame we want it in, which is with respect to the Earth frame, which is E. Okay, so the BKE then, the process is we first take the derivative of all the points with respect to the frame they're written in. So because these are written in two different frames, I need to split them up when I do the BKE. So I'll first be doing the BKE of L A1 hat plus H A2 hat minus D A3 hat. And then I'm going to be doing the derivative with respect to the E frame of R B1 hat. Okay, and then let's just look, okay, let's like split this into two terms so it's easier to look at. So, oh, I should color code this, because that would be helpful. Okay, I'm going to call this 1, and then I'm going to call this one 2. Because now they're in the same color code as the frames. I guess it's not necessary, but looks nice. So when I first do the derivative of the first term, I first take the derivative with respect to the A frame. So that is going to be equal to L dot A1 hat plus H dot A2 hat minus D dot A3 hat plus the angular velocity of the A frame with respect to the E frame crossed with the original vector, which is this, right? So obviously, like, this rod is not expanding or contracting, you know, that would be a bit crazy. So we can just ignore these terms, right? Because the lengths are not changing. So those will become 0. What's the angular velocity of the A frame with respect to the E frame? Well, the A frame is like is the rod is fixed in the rod, and the rod is rotating like around here like this. So we can do right hand rule. So if we take our right hand, curl it in the direction of the rotation, which is like around this like axis here, you can verify that your thumb should be pointing down. So it's pointing opposite the A2 hat direction. So the angular velocity is going to be omega 1 in the negative A2 hat direction. So negative omega 1 A2 hat crossed with L A1 hat plus H A2 hat minus D A3 hat. And then you can do whatever cross product you prefer. Shoot, wait, what was it? You like 1, 2, 3, 2, 1? Or is it 1, 2, 3? 1 cross 2 is positive. Okay, I'm sorry. I'm trying to remember like that trick. 2 cross 3 is also positive, and 3 cross 1 is also positive. Wait, 3 cross 1? Yes, I think so. Okay, point is you figure out like the signs, and you should be getting like omega 1L A3 hat. So this would be, okay, I'm sorry, I have to do determinant. 0 negative omega 1 0 L H negative D A1 A2 A3. Okay, so I think I explained this in like some of like another video. Oh, something dropped. Okay, well, I explained this like in another video at some point. But the way you can do this, one way you can do the cross product is through the determinant method. You take this column, you get rid of it, and then you just do the cross product between the remaining terms here, and that's going to be your value in the A1 hat direction. And then you do the same for the other ones, except for A2, you have to negate the result. So that's one way of doing it. The other way is this method. So I think like, I always forget. So I think 1 to 2 is positive. So if you have a 1 vector crossed with a 2 vector, like A1 cross A2, you should get a positive A3 hat. Then if you do 2 cross 3, it should be positive. And then for 3 cross 1, it should be positive 2. And then if you go the opposite way, it's negative. Oh, actually, that's not as bad as I thought it was to remember. Okay, anyways. Okay, sorry, that was a really long detour. Let's just go back to the problem. So now we can do, we have A2 cross A1. So that gives us a positive omega 1L. And then A2 cross A2 is going to be 0. And then we have omega 1D A2 cross A3, which is positive. So that's going to be positive A1 hat. And that seems right. Yeah, so that's correct. That's our answer for not our answer. That's our value for part 1. So we go to part 2. So this is the derivative of r b1 hat. So that's going to be equal to r dot b1 hat plus the angular velocity of the b frame with respect to the e frame cross the original vector, which is r b1 hat. So I don't think it mentions in this well, the radius of the disk is not changing, and point P is not said to be moving anywhere like along the disk. So we can safely assume that r dot is equal to 0. So the time derivative of the radius of the disk is equal to 0. Now we need to find what omega b with respect to E is, because we have a complex rotation. So remember that the disk is rotating with respect to the rod, which is rotating with respect to the ground. So this means that the angular velocity of the disk with respect to the Earth is going to be equal to the angular velocity of the disk with respect to the rod plus the angular velocity of the rod with respect to the Earth. Okay, what is this? So we found out this term, right? This term was equal to negative omega 1 A2 hat. And then we also need to find omega of B and A. So the B frame is rotating with respect to the A frame at this angular velocity of omega 2 this way, right? So that was stated here. This is measured relative to the rod. So because relative to the rod, we have omega 2 being the angular velocity from the B frame with respect to the A frame. Okay, so what direction is this in? So we do our right hand rule. Curling our fingers in the direction of omega 2. Our thumb is pointing out, should be pointing out of the disk. So it should be pointing the opposite direction of b3 hat. So the angular velocity is going to be negative omega 2 b3 hat. Negative omega 2 b3 hat. Okay, and then this is like cool, but it's also not cool because we have the angular velocity in two different frame unit vectors, right? A2 and then b3. And we cannot just like cross product these terms. So one way you could do, so one option is to change all the, okay, so sorry, let me just actually rewrite this now that we have our answer. So we now have negative omega a2 hat minus omega 2 b3 hat crossed with our b1 hat. Now, you see the issue again is this a2 hat term. You could convert all of them into the b frame or all of them into the a frame. But personally, I think it's easier to convert everything into the b frame. So that's what I'm going to do with this. So I'm going to convert a2 hat into b hat terms. So what does a2 look like? So now we need to do vector projection. So let's think about this. So let's just like think about like it is as if we're on the rod and we're like looking at this disk spin. So I'm like gonna just put myself here, here, and I'm like looking this way. So what I see then is that over time, this b1 hat and then b2 hat, like this is me looking at the disk face on, they're gonna be like rotating, right? Because the disk is rotating relative to the rod, and if I'm standing on the rod, I see the disk is rotating. So at some time, maybe, I will see it being like this. B1 hat, B2 hat. Okay. And then because I'm on the rod, to me, the rod is not moving because I'm on the rod, obviously. So that means that to me, I see that this B1, B2 hat is rotating in this direction. Meanwhile, the A2 hat and A1 hat vector are always going to be like this. So I hope that makes sense. What I'm trying to say is that if I'm like standing on the rod, I see the disk frame, the B1, B2 hat vectors constantly rotating. Or not constantly rotating, just like rotating. And the A1 and A2 hat are always going to be in this direction, right? In this direction along the rod. So this is what gives us our vector projection. It's from looking at the disk face on and then thinking about how the A1, A2 hat vectors and the B1, B2 hat vectors look in comparison with each other. So this means that the B1, B2 hat vectors are offset at some angle from the A1, A2 hat vectors by some angle, which I'll just call theta. Okay. So that's our vector projection. So let's think about how we can write this A2 hat vector in terms of the B frame then. So I'm going to redraw that down here. So I should use different colors. So A2, B1, B2, and like these are perpendicular, right? So B1, B2. Then A1, which is not really, okay, like you really don't need to know what A1 is, but I'm just going to draw it here so for the complete picture. So this is theta, and this is also theta. Okay, so how to write A2 hat in terms of the B terms. I think something that helps me sometimes, because I it's hard to visualize some of these things, is to just like move it so that the B1 and B2 hat are like flat with the page, and then it's like the A1 and A2 hat that are like at an offset. So like all I did was like I took this image and I just like flipped it a little bit, and that's what gives me this image. So now my A1 is this way, A2 is this way, and the angle between them is theta, theta. Okay, so now hopefully from like just trig you can write the vector a2 hat. So a2 hat is equal to negative cosine theta b1 hat plus negative sine theta b1 hat plus cosine theta b2 hat, right? Because the cosine is along here, the sine is along here. Okay, so that's cool. So now we can rewrite this expression as negative omega 1 times negative sine theta b1 hat plus cosine theta b2 hat, right? I'm replacing the a2 hat, minus omega 2 b3 hat crossed r b1 hat. Okay, and now we can do the great product stuff. So we have a b1 hat cross a b1 hat, which is just going to be 0. Then we have a b2 hat cross a b1 hat, which will be omega 1 cosine theta times r positive. So yeah, okay, yeah. So that'll be in the b3 hat direction because b2 cross b1 would be negative, but then that negative cancels this negative here. So we have that term. And then we have b3 cross b1, which will be omega 2 r, right? Because b3 cross b1, so it's b2. 0 minus this, which is positive, but then you have to negate it because b2 term. Okay, yeah, so this should be a negative b2 hat. Is that right? Yeah, that should be right. Okay. So now we have our two terms for the velocity. Oh my gosh, are we just on velocity? Okay, yeah, okay, this should go faster now, but from that we can write our expression for the velocity, P and E, as omega 1 L A3 hat plus omega 1 D A1 hat plus omega 1 R cosine theta B3 hat minus omega 2 R B2 hat. Okay. And then I think we can just like plug in the values now. So we got from above that omega 1 equals 3. Let me write this down. So omega 1 equals 3. And then I think we had L equals 2. D equals 0.5, 1.5. Okay. 0.5 meters. So all these are meters. Did I just like lose an H? Wait, hold on. Oh yeah, we don't need the H. Okay. And then R equals 0.5 meters. So our expression becomes omega 1 times L, which is 3 radians per second, times 2, which is just 6 A3 hat, plus 3 times 0.5, which is just 1.5 A1 hat, plus omega 1 R cosine theta. So omega 1 times R is also 1.5 cosine theta B3 hat minus omega 2. Oh, wait. I'm so sorry. Okay. Wait, actually, am I just trolling? Oh, never mind. Okay, so sorry, we're good. I forgot the omega 2 existed. So the omega 2 is equal to 4 radians per second. Alright, so minus R times, so that's 2 B2 hat. And then these are all in units, going to be in meters per second, right? Because radians is not technically doesn't have any dimension. And then we're like, oh no, what is going to be happening with the theta? Well, as it says in the problem, we have this at this instant. So that instant is when point P on the rim is at the same horizontal level with the center of the disk. So that means that P, the distance from here to here, is going to be parallel to the A1 hat because they're on the same level. So that then means that the angle between the A1 and B1 vector is going to be 0 because they're on the same horizontal levels. So P is always, like, this is the center, this is P. For them to be on the same level, they have to be parallel to A1 hat. So that means theta is equal to 0. So that's going to be equal to 0 at this instant. So that just gives us 6A3 hat plus 1.5 A1 hat plus 1.5 B3 hat minus 2 B2 hat, and then meters per second. So this is the velocity of point P with respect to the E frame. Okay, now let's do the next part, which is the acceleration. Okay, I guess we can just keep going with this. So the question is then, do we just take the derivative of this? Which the answer is no, because this is the velocity at the instant. This is not equal to the general expression for velocity. This is the general expression for the velocity. And then we apply like these conditions, like theta equals 0, to to find the velocity at a specific instant. But you cannot just take the derivative of this expression, obviously, because there is acceleration happening, and we just need to account for that in the general, using the general expression. So the acceleration of point P and E is equal to the time derivative of the velocity of point P and E. And that is just going to be equal to the... I'm again going to split up this into the A frame terms and the B frame terms. So the first term is omega 1 L A3 hat plus omega 1 D A1 hat plus time derivative of omega 1 R cosine theta B3 hat minus omega 2 R B2 hat. Okay, so this is our expression for the acceleration. We just do what we've always been doing, and we just start going crazy with derivatives. So I'm again going to split this up into the first term and the second term. So term 1, term 2. So in this first part, we have... okay, so I'm just going to skip over, I guess, this part. Well, not skip over, but just like rush through this part a little more now that we're comfortable with it. But we know that omega 1 is constant. L is constant because the rod's not like going crazy and changing length. So we also know the same thing for D. So this means that the derivative of this expression with respect to the A frame, which is the expression for BKE, this is just going to be 0. Plus the angular velocity of the frame it's written in, which is the A frame with respect to the E frame, crossed with the original vector. So that's omega 1 L A3 hat plus omega 1 D A1 hat. And then we already know omega of the angular velocity of the A frame with respect to the E frame is negative omega 1 A2 hat, I believe. I think it was A2 hat. Yeah. Negative omega 1 A2 hat crossed with omega 1 L A3 hat plus omega 1 D A1 hat. And then this will just give us omega 1 squared L A1 hat. So the negative A1 hat direction plus omega 1 squared D A3 hat. That makes sense because like A2 cross A1 would be negative and then negate that, which is a positive. Okay, so this is the first part. The second part of that expression is going to be a little more messy. but we'll persevere again. So we have the time derivative of this expression with respect to the frame it's in, which is the B frame, plus the angular velocity of B with respect to E, crossed with the original vector, which is omega 1 r cosine theta B3 hat minus omega 2 r B2 hat. Okay, so omega 1 is constant, r is going to be constant, but omega 2 and theta is not constant. So we have, because theta is like the angle that the B frame rotates through, but we know that it rotates through some non-constant angular velocity omega 2, because that's what it was just saying in the problem statement, right? It says that the disk is rotating with omega 2 equals 4, omega dot 2 equals 2. So that means that it's rotating with some non-constant thing. So theta, the time derivative of theta is just going to be the angular velocity. So I'm going to write this now as omega 1 r, because that's constant. And then the derivative of cosine theta is going to be negative cosine, or negative sine theta. And then we apply chain rule, so we get theta dot B3 hat. And then minus omega 2 r, r is constant, omega 2 is not constant, so we have omega 2 dot times r B2 hat. And then we do plus the angular velocity of B with respect to the E frame. I think we figured this out like up here to be, yeah, so we found this here, right, to be this. And then we did that whole conversion thing where we converted the A frame into the B frame. And this is the final expression we got. So I'm just going to like copy this over. Copy. Okay. Technology is crazy. Okay. Uh-oh, unless it breaks my computer. Okay, that's not ideal, so let's move this back. Okay, so that's our omega B and E. And then we cross that with this ugly expression. So we cross that with this. And I'm not going to write that in just so we can like figure things out step by step. Okay, so theta dot, first of all, is just going to be equal to omega 2, right? Because that's the rate. So theta, as I said before, is the angle that the B frame is rotating through, like this B1, B2 is rotating through, like the disk is rotating like this. So the angle that's rotating through, the change in the angle it's rotating through with respect to time is just going to be omega 2. So I'm going to have negative omega 1, omega 2, r sine theta. Sine theta. B3 hat minus omega 2 dot r B2 hat plus, okay, I'm going to bust out the determinant now because this is a little too much for me and I don't have the brain power for this. So we have B1 hat, B2 hat. And honestly, I feel like when the expressions get super messy like this, the determinant just like makes it easier because it just automatically groups things for you. So I'm going to take the first term, which is our omega B and E, so which is this whole thing. So that becomes omega 1 sine theta. And then negative omega 1 cosine theta. Negative omega 2. So that's like the first term. Wow, this problem has gone so long that my laptop is breaking under its length, I guess. Okay, so now we put the second term in. Please work. Okay. Okay, so now and that I just put the second term right here, which is what you would do to find the cross product. Okay, so this cross product ends up, so I'm going to write this here. So negative omega 1. Okay, actually, okay, yeah, actually it's fine. So sine theta b3 hat minus omega 2 b2 hat plus, so this becomes, okay, in the b1 hat direction, I would cross out this column and then take the cross product between these two. So that would give me negative omega 1 squared r cosine squared theta, and then minus negative omega 2r times negative omega 2, which is just minus omega 2 squared r. And then that's just in the b1 hat direction. Okay. Okay, sorry, you're gonna have to deal with the lag from my computer. And then we do the next term, which is the b2 hat term. But remember, because it's the b2 hat term, you have to add a negative sign in front of it. So we have negative, the determinant of these remaining four terms, which is just omega 1 squared r cosine theta sine theta. And that's in the b2 hat direction. Yes. And then we have the final one, which is the b3 hat, which is we take this column, remove it, and then we calculate the remaining determinant, which is just omega 1, omega 2, r sine theta, r sine theta. I think I missed a negative. Wait. Yeah, okay, yeah. So that's b3 hat. Okay, so this is our second term. And what I'm actually going to do, so I'm going to simplify using the instant info. So, right, like we did above, we have everything at the instant. So now that we finished taking the derivatives and everything, we can just start plugging in the values that we know to find the acceleration of that point P at that instant. And we know that at that instant, theta is equal to 0, right? So this means that our sine terms all become 0, which is great news. So we can start xing those out. So theta equals 0. So this means that this term becomes 0, this term becomes 0, this term becomes 0. And this just becomes a 1. Okay, so now that expression becomes just negative omega 2 dot r b2 hat minus omega 1 squared r minus omega 2 squared r, or plus b1 hat. And that's actually it. Okay, that's pretty nice. So that's our expression for the second part and the first part. So when we combine this and this, so this and that, we can get that the acceleration of point P with respect to the E frame is equal to negative omega 1 squared L A1 hat plus omega should be a 1, omega 1 squared D A3 hat. and then minus omega 2 dot r b2 hat minus omega 1 squared r plus omega 2 squared r b1 hat. Okay, and then we can plug in our values. So we have omega 1 is equal to 3. So we have, omega 1 equals 3, L equals 2. D equals 0.5. And then omega 2 equals 4. So negative omega 1 squared, L is negative 18. And then omega 1 squared D is 9 divided by 2, which is 4.5. A3 hat. And then minus omega 2 dot, I don't remember what that is. So omega 2 dot is 2. So 2 times r is 0.5, so it's just 1 b2 hat. And then minus omega 1 squared plus omega 2 squared times r. That's not, so that's going to be 25 times 0.5, which is 12.5. Yeah, 12.5 b1 hat. Okay, this is going to be our, and this is all in meters per second squared. So this is our final expression for the acceleration at point P with respect to the E frame. Okay. Okay, and now I'm going to switch to doing the velocity expansion method, which actually I think will be much easier, so yeah. Okay, so this is the velocity and acceleration expansion version of this problem. So you might ask, why would we use this method? And the reason is because you're finding something at an instant. So you have an instant condition here where P is at the horizontal level as the center of the disk. And when you use velocity acceleration expansions, you don't have to do all the derivative stuff, and it's very tedious. So it's much easier if you can just plug in that instantaneous condition directly into these expressions, which is what the power of kinematic expansions are. So in this case, how does this work? Just a brief refresher. If I have some point P of interest and I want to find its velocity with respect to the fixed frame, and let's say it's just much easier to consider this from this reference frame G, and it's much easier to find the velocity of this point in the G frame. And then when you do that, you need to pick a point, capital G, that is fixed in this G frame. So how does that translate to what we have here? So in our case, we want to find the velocity of the point P with respect to the E frame. And to do that, we need to find some point, which I'm just going to call capital B, that is fixed. So let me take a step back. So, and let's just say that we know it's super easy to find the velocity of point P with respect to the B frame, right? Because if you're in the B frame, you're rotating with a disk, point P is not moving, obviously, with respect to the B frame. It's just a stationary point on the disk. And so that means that we would be able to find this value very easily. So let's just say we want to then find some point that is fixed in the B frame as our capital G point. And this is again because we want our we find it very easy to find the velocity of point P with respect to the B frame. So that means we need to translate this expression into the terms we're using. So first we find the velocity of the point P with respect to the E frame. Then we need to find the velocity of our fixed point, which I'm just going to call capital B, with respect to the E frame, plus the angular velocity of the frame that we are finding the velocity of P very easily in. So that frame is going to be frame B. So we have the B frame with respect to the E frame, crossed with the distance between the fixed point in the B frame to point P, plus the velocity of point P with respect to the B frame. So quick just recap, we just picked point B that is fixed in the B frame because we know it's very easy to find the velocity of point P with respect to the B frame. So now we need to pick the point B that it's fixed in the B frame. Well, obviously this point is not moving with respect to the B frame because it's like the origin of the coordinate system. So it would not be moving. And this is actually a really nice point to pick too because it makes our position from B to P very nice and easy to calculate because it's just going to be R B1 hat. So I'm going to call that point B. So the velocity of B with respect to the E frame is given by the following. So you can find this, like, I guess, in two different ways. One way is you can do some BKE. So you can just say, oh, well, the velocity of point B with respect to the E frame is just going to be the time derivative of the distance from some point O to B with respect to the E frame. And then I'm going to add all the other stuff in. So the angular velocity of the B frame with respect to the E frame is, oh, we found this before, and I'm not going to write it out in full, but if you go to the first part where we used BKE, we did find the angular velocity of B and E. It was through the complex rotation stuff. And then we have RBP, which is just going to be RB1 hat, right? Because going from B to point P, you just go a distance R along the B1 hat direction. And then the velocity of point P in the B frame is going to be 0. Because we already said that P is not moving in the B frame. Okay, so now we have this here. So we have, to find the velocity of point capital B with respect to the E frame, we have this expression here where we need to do BKE. So I think like before, we had picked point O, which is a point that is fixed in the E frame, as being that point there. So from O to B, it would be L A1. Also, if you like skip to this part of the video, just know that I go through like the variable names and everything in the part where we do the BKE method. So I think if you go to the beginning of that, I explain where everything is coming from. So we need to take this is the expression from O to B. So do this, and in this process, I'm going to actually probably go faster because we've already done a lot of stuff like figure out what the angular velocity of B and E is. So I'm just not going to go through that again. So then we have angular velocity of B and E, which, I actually did this cross product before, so I'm just going to copy the result of this cross product, but I'm going to copy the result of this cross product, but you can just go back and see. I'm actually at the end of this video, I'm just going to go through, just slowly scroll through the entire thing so we can just all see the work in chronological order. But this is the expression that we get from the cross product. Okay, and this expression, I actually think we found this too. It ended up being like omega A and E crossed with the original vector, which ends up being omega 1 L A3 hat plus omega 1 D A1 hat. And then we include the other stuff, so omega 1 R cosine theta B3 hat minus omega 2 R B2 hat. Okay, and then we can plug in our values and then that initial instant condition. So omega 1 was 3, L was 2, so this is 6 A3 hat. And then plus, so 3 times 0.5 was 1.5 A1 hat plus omega 1 R, which is also 1.5. Remember that at that instant, so at the specific instant, theta is equal to 0, so we just are left with 1.5 B3 hat minus omega 2 times r, which is 4 times half, which is 2, b2 hat. So this is our expression for the velocity of point P and E, and this is good because it matches with what we got earlier. So yeah, acceleration of P and E. So this is pretty much the same thing, and now we just replace all our G's and capital G's with the B's. So I'm gonna just like copy that down. So we have acceleration of point B and E plus the angular velocity of B with respect to E crossed with angular velocity of B with respect to E crossed R capital BP plus the angular acceleration of the B frame with respect to the E frame crossed with R capital BP plus 2 angular velocity of B and E crossed with the velocity of P in the B frame plus the acceleration of P in the B frame. Okay, that is quite a lot. Let's just make sure A1, 2. Okay, I think I got all the terms. Okay. Okay, so now we can start doing stuff with this. So first things first. This is kind of a lot. It's a little overwhelming, so let's just look at this term by term. First thing to remember is that the velocity of P in the B frame is going to be 0. If the velocity is always 0, then the acceleration is also going to be 0. So this is great because that means we can eliminate these two terms entirely. So V, P, and B is equal to 0. And then velocity of, or the acceleration of P with respect to the B frame is equal to 0. Okay. Now we do start getting to the muddy parts. So this is equal to acceleration of B and E plus the angular of B and E cross the angular velocity of B and E cross R BP. So we said that B is this point here. So from B to P, it's R B1 hat. I think my computer just like breaks every time we get to acceleration expansion, which is not entirely not valid because this is quite messy. So now we just need to figure out what these terms are, which we definitely have some of them. So let's see. So I think I'm going to just copy down the expression for the angular velocity of B and E, and of B with respect to E. So that one we found to be, this is again a lot from part 1. So that's omega 1 sine theta B1 hat minus omega 1 cosine theta B2 hat minus omega 3 B3 hat. Yeah, okay, and then that's one of them. The other one is the acceleration of point B with respect to the E frame. Okay, so let's see. So we previously found that the velocity with respect to the B frame, we found the, let me do this. So we found that the velocity of point B with respect to the E frame is this. So the acceleration of point B with respect to the E frame is just a time derivative of the velocity point P with respect, or sorry, not P, point B with respect to the E frame. Yeah. And that is equal to the time derivative of omega 1 L A3 hat plus omega 1 D. Oh dear. I hope my computer can pull through. A1 hat. Okay. And then that is going to be equal. We apply BKE. So I guess you can't escape the BKE too much. But we know that the omega 1, L, and D are all constants. So that initial derivative with respect to the A frame becomes 0. And we're just left with omega of A and E cross with the original vector, which due to my computer overheating right now, I'm just not going to write out in full. It is just this expression in here. And that should give us, so omega A and E was negative omega 1 A2 hat. Crossed with this. And that will give us, so it will give us omega 1 squared L A1 hat. I think there should be a negative. And then, yeah, so then we have A2 cross A1, so that's a positive. Wait, yeah, that gives a positive omega 1 squared times D A3 hat. Okay. That's our expression for the acceleration of B and E. And then finally we have the angular acceleration of B and E. So this is just going to be equal to the time derivative of the angular velocity of B and E. And that we know from up here. I can just plug that in. We have to apply BKE again. So first we have the derivative with respect to the B frame of the original vector. So that gives us, so I guess just to write this out for completeness, the time derivative with respect to the B frame, omega B and E, plus the angular velocity of B and E crossed with the original vector, which is the angular velocity of B and E. So this obviously becomes 0 because we're just cross-producting the vector with itself. So we're just left with the time derivative of this with respect to the B frame. So omega 1 is constant, so then we have the derivative of sine theta, which is cosine theta times theta dot B1 hat minus plus, because derivative of cosine is negative sine, times theta dot, and then, whoa, where did I get this omega 3 from? Oh, this should be omega 2, sorry. So this B2 hat, and then minus omega 2 dot B3 hat. Okay. And what are we doing? Okay, so great. That will give us, so theta dot, remember, is equal to omega 2 because that's the rate of change in angular and the angle that the frame is rotating through. So we have omega 1, omega 2 cosine theta B1 hat plus omega 1, omega 2 sine theta B2 hat minus omega 2 B3 hat. Okay. So now we have our three things, and here's like where the power of acceleration expansion comes in. We want to find the acceleration of point P at this specific instant. So remember that at this instant, theta equals 0. So I can actually just directly plug in this theta equals 0 right into all these expressions. So these three expressions. So what does that give me? Sine theta is equal to 0, so this becomes 0. Well, yeah, that becomes 0. This becomes 1, right, because cosine of 0 is 1. This becomes 0, and then this becomes 1. So now my expression right here, it becomes much nicer. It just becomes negative omega 1 squared L A1 hat plus omega 1 squared D A3 hat. So that is the that is this term. This term is equal to this, and then I have plus. Okay, now I have omega b cross r. So that's going to be, now in my simplified expression, it's going to be negative omega 1 b2 hat minus omega 2 b3 hat crossed with negative omega 1 b2 hat minus omega 2 b3 hat crossed with r b1 hat. That seems correct. Okay. And then I add my acceleration term, which is now just omega 1 omega 2 b1 hat minus omega 2 dot b3 hat crossed with r b1 hat. Okay. Okay, let's simplify this expression. So, okay, so I'm just going to start plugging in the numbers. So we know omega 1 is 3, L is 2, so this is going to be negative 18 A1 hat plus 9, so 4. Excuse me. Okay. And then, okay, so we have this cross product thing going on. I'm just going to make this as a little side story. So this is going to be equal to so this is equal to negative 1. Okay, let's just do this. So this is equal to omega 1 r b3 hat plus minus, wait, omega 2 r b2 hat, but which direction is it? So b3 cross b1 will give you a negative, and then you have another negative, so it negates it, so it's a positive. Okay. And then you have that crossed with this, so we can do... okay, sorry this is not very clear. Let me just do this. So then, okay. So we have negative omega 1 b2 hat minus omega 2 b3 hat crossed with omega 1 r b3 hat plus omega 2 r b2 hat and then we have this term, and that term just evaluates to omega 2 dot r b2 hat, which, wait, is that negative or positive? Positive, yeah. And then omega 2 dot is 2, and then r is equal to 1, so this just becomes 0.5 times 2, which is just 1. And then we can do this cross product, so this cross product is just so omega 1 squared r b1 hat. So like, I guess like one way you can do this is a determinant method. Otherwise you could do it as like this distributive method, I guess. So we have b2 cross b3, which gives us this term. And then b2 cross b2 is just going to be 0. And then we have B3 cross B3, which is 0, and then B3 cross B2, which is squared R B1 hat. Wait, let me check my negatives real quick. Okay, B2 cross B3, so this should be a negative. And then B3 cross B2 is negative. It seems as though I have made a negative sign error, which is very unfortunate. Okay, I think I found my mistake. So the issue is right here. I should never be trusted to do cross products. This should be a negative. So let me just erase that and then make that change. This should be a negative. Now it gives you a positive B2 hat, so that's why when you negate it, it should be a negative. Okay. Point is, don't trust me with this cross product stuff. I should always do determinant method because I can never get it right. Okay, so now I'm going to change this to, so this should be a negative sign. Okay, and that should actually give me the right answer now. So I have negative omega 2 B3 hat cross negative omega 2 R B2 hat, which gives me negative omega 2 squared R B1 hat. Wait, does that make sense? Yes, it does. Okay, great. So now my final result is negative 18 A1 hat plus 4.5 A3 hat. And then this omega 1 squared R minus omega 2 squared R is going to be equal to like 3 squared times 0.5 minus 4 squared times 0.5, which is just 25 divided by 2, which is 12.5. And then plus 1 B2 hat. Oh, did I mess up the signs again? Okay, yes I did. Okay, I should just stop doing cross products like that. So this was a positive, it should be a negative. Because B3 cross B1 gives you a positive, but then this negative here negates that, so it becomes a negative overall. So this is a negative 1 B2 hat. Okay, and then this is all in terms of meters per second squared. So this is the expression for the acceleration of point P with respect to the E frame, and this was done using the acceleration expansion method. So again, like the key thing here that saved us so much, well, I don't know, I guess it depends on what you think is saving a lot of time, but this giant expression here, we simplified a lot of it because we could figure out that some things were equal to 0 based on the velocity of this point P in the chosen frame we used, which is the B frame. And then also we were able to just instantaneously plug in the expression at the certain instant we were interested in into all of these expressions. And so that made our lives a lot easier because we could just simplify them to very much easier like terms. And that helped our cross product stuff and everything. So, and that is why like the kinetic expansions are so powerful. But to be honest, they're also very easy to make mistakes, and sometimes they can be very tedious. So I think that's all. I'm going to actually just do a quick recap. If you want to listen or not, that's also okay. I'm going to scroll through the work pretty slowly if you want to just like look at the work too. Okay, recap. We first established 2 frames for the 2 specific rotations. So we have the A frame in the rod and the B frame, which is in the disc. When we apply BKE, the first thing you do is you find this point that is fixed in the ground frame, or the frame you're interested in taking the and finding the velocity with respect to, which in this case was the Earth frame. And we find an expression for the position from that fixed point to the point of interest, which is point P. And we wrote that in terms of the A and B frame. Then we performed BKE and did all this math to get this final result. And one of the key steps that we did was to do this vector projection thing right here, to convert all the quantities into the same reference frame terms. So when we did that, we were able to get an expression for the velocity, and using the information we were given in the problem, which we also defined these variables to represent the lengths, we can plug it in the velocity at the specific instant, which was when theta equals 0, and we can find the velocity. And the way we found theta equals 0, if you remember, is by recognizing that for P to be horizontal with the center of the disk, you need to have this angle between the A1 and B1 vector to be 0. And again, just remember, this projection is just based on how we look, like let's just say we're looking face on at the disk, and how does the A frame and the B frame look. So that was how we did the vector projection. And then we did pretty much the exact same thing, which is just BKE, take the derivative of the velocity vector to find acceleration. And that didn't really give us anything new. We just did the same kind of thing with the math and everything. And we simplified it, and then we got the final expression for the acceleration. And the BKE method is honestly pretty straightforward. It's just a bit tedious with all the differentiating we had to do here, like for example here. But yeah, this is how we did the BKE method. So I'm just going to scroll through from the top. Okay. The next method we did was the kinetic expansion method. So the difference between this is you really just need to just plug and chug into these two formulas, and you need to just find a point that is fixed in a frame that is easy for you to find the velocity or acceleration of some point of interest with respect to. So for example, we know that it's really easy to find the velocity of point P or the acceleration of point P with respect to the B frame. And because of that, we choose the B frame as the frame that we do stuff with. And we found point B, which is right here, to be the point that's fixed in the B frame, because that's how the expansion formulas work. So we have this, and we're going to apply the expression for the kinetic expansion. Unfortunately, you can't escape BKE forever, so we had to do a little bit of stuff with the BKE to find the velocity of point B with respect to the E frame. But we had already figured out a lot of these expressions prior from the BKE part, so if you just refer back to the videos, you can figure out what those expressions resulted in, or you can just redo them yourself to make sure you understand. And we were able to get the velocity expression. We would do the exact same thing with the acceleration, and we were able to simplify a lot of the expressions because we know that the velocity of point P within the B frame is equal to 0. And similarly, we actually simplified a lot because we were able to apply this information about what we want to find at a certain instant, which is when theta equals 0. We use this to simplify our expressions for the angular velocity, the angular acceleration, and the acceleration of point B and E, which we were allowed to do because this is just a direct expression. This acceleration expansion is a direct expression for the acceleration. So we don't need to do, so there's no issue with differentiation that we have with BKE. Because of that, we simplified everything, and then our cross products occurred, some mishaps occurred, but we end up with this expression which matches that of the BKE, so we can verify that this is these answers match and these are the correct expressions. So again, I'm going to just scroll through very slowly. Okay. And yeah, that was the exam, so yeah, hopefully that wasn't too bad. Okay, see ya.